Now, what I'm going to do is, to start you off with an example, because that's honestly the best way, I want to start by drawing just a simple, maybe not so simple, but an example compound to illustrate the point of sort of resonance. Okay. So just give me 1 second. Okay, so this is an arguably very complicated compound. I don't know why I said simple before. And this molecule does have ultimately some resonance in it. Now, there's a trick that I learned when I was teaching aromaticity, and it relates to aromaticity very well in terms of how to identify if you have conjugation of electrons in a system. But one thing this rule also tends to work for is also identifying whether or not there's resonance in a molecule. And here's one thing I want to show you, and this may not make a lot of sense at first, but as we progress through it, hopefully it will. We know that this right here, this entity right there, that's a double bond. Take, for instance, another part of the molecule. This right here, this is going to be a single bond, essentially. So what I'm going to do is I'm going to denote all of the double bonds by a D, and then I'm going to denote all single bonds by an S, okay, at least in this form of the molecule. So if I do that, here I have a double bond. I'm actually going to put it right next to the bond. This is a double bond, single, double, single, double. Here's a single bond, and then here's another single bond. And then what I'm also going to do, there's two other things I want to be able to identify. If I have a lone pair, in other words, the lone pair is on this carbon right there, I also want to make a note of that. So I have a lone pair there, and a single bond there, double bond, single, double bond, single. Here's another single bond, a double bond, a single bond, a double bond, single bond. The other thing I want to take into account is the carbocation. I'm just going to denote that as Cc. Okay, so if you're ever pressed with some kind of organic question on an exam or quiz, and they say, where is the resonance in this molecule? This is sort of what you would do. And honestly, they probably wouldn't give you a molecule this big. I would label all the double bonds and single bonds in the way the molecule was drawn, and then also indicate a lone pair, if it's usually between two single bonds, and then any carbocations, usually I do that as Cc. So here's kind of the rule to know if you have any kind of resonance. So in this first stretch of the molecules, I start over on this side over here. You notice I have this pattern. I go double, single, double, single, double, single, single. Well, here's kind of a rule. Anytime you have a repeating pattern of double, single, double, single, double, single, on, and basically repeating ds, 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 then all the pi electrons that are in the double bonds, okay, those pi electrons are in resonance with each other, okay? They're in resonance with each other. One rule of thumb is that if you have two single bonds right next to each other, so you could have, in other words, double, single, single, double, and so forth, then the pi electrons in this double bond and the pi electrons in this double bond are not in resonance with each other, meaning the pi electrons over here cannot be delocalized over here because, notice, they're separated by two single bonds right here, okay? Whereas, notice here between, say, this double bond and this one, they're only separated by one single bond, the same case as it were in the case of this one and this one, they're also separated by one single bond. Okay, so if you have double, single, double, single, double, single, double, on, and on, then the pi electrons in those double bonds are going to be delocalized over each other, and you have resonance through that system. But anytime you have two single bonds in a row in the molecule, you have what's called a discontinuity, and the resonance is broken over that length, meaning that you can't sort of what they call jump electrons across the two single bonds. It can only be potentially over one single bond. Now there's another pattern you can have. Let me just kind of do it generically. Suppose now, for example, you have a double bond, a single bond, and then let's say, for instance, you run into a lone pair. Then you have another single bond, double, single, double, and so forth. Well, one thing you can actually look at is that number one, this double bond and this double bond, okay, they're separated by only one single bond. So it turns out these two, the pi electrons in these two double bonds are going to be in resonance with each other. There's a lone pair here that it goes lone pair, single, double. And on this side, it goes double, single, lone pair. What we can also say is that the lone pair right here is in resonance with these pi electrons over here, and also this one over here, because once again, the lone pair is separated from each double bond by just one single bond. Okay, so in other words, when you're looking at this kind of pattern, the lone pair is going to kind of function in a similar way to the double bond, as it were, in this first series right here. Okay, and that's actually what we see right here. Notice, I'll do this in an orange color. We have single, lone pair, single, and then double, single, double, single. Now, if you look here, notice once again, these two double bonds right here, so this one right there and then this one right there, the pi electrons there are separated by one single bond and then a second single bond. So two single bonds. Therefore, that's what we call a resonance discontinuity. There's no way that these pi electrons right there can be delocalized in this area right there, because there's this discontinuity that results from two single bonds. Okay? And there's one other thing to kind of look at, and that's in the case where you have a carbocation. So let me do this kind of in blue. So let's suppose, again, you have something that takes on the form of maybe, let's do double, single, double, single, and then instead of a lone pair, let's throw in the carbocation, which is just the plus charge, the carbocation, okay, and then you have maybe single, double, okay. Well, in this case, notice, here I have single, I have a double bond, a single, a double bond, a single, and then I have this carbocation right here at the end. And the carbocation, in the case of resonance, is going to, at least in this series, is going to behave very similarly to the lone pair. And so essentially what you can show is that, for example, the pi electrons in this double bond and this double bond are actually delocalized to the carbocation, and also the pi electrons in this double bond over here on the left are going to be delocalized to that carbocation as well. So if you're looking in a molecule to find sort of a distance of the molecule where the resonance is not broken, you follow basically these patterns right here, and notice that the lone pair is going to function kind of similarly to the carbocation. So that's sort of a very abstract way of looking at it. What I want to do now is look at these specific examples. So right here, here's this molecule. I'm going to redraw it down here, and then we'll take a look at it. So this is a really simple molecule. Notice what kind of pattern this has. Okay, if we kind of dissect this, this has a characteristic. Let me do red. This has double, single, carbocation. Well, if we look at the pattern, we notice that the carbocation is separated by the double bond by only a single bond. Okay, and so when we notice that pattern and it corresponds to the one we just saw up here, we note that there's going to be some resonance in this molecule. Okay, and I'm just right now concerned on noting whether or not there is resonance. Later on, we'll actually look at how to draw the resonance structures. Okay, then we have this molecule up here. It's kind of similar, except it has extra electrons. It has a lone pair. So we have this double bond, and then we have a lone pair right there. Well, we're going to kind of look at the same pattern. We have a double bond, a single bond, and then we have a lone pair. And we notice that that pattern, or that series, gels pretty well with this right here, at least this part of it, double, single, lone pair. And so therefore we can also say this molecule is also going to have some resonance. I also want to look at this third compound right here. Okay, this one has two double bonds. Okay, And let's take a look at the pattern that emerges when we characterize this. This has double, single, and then it ends in a carbocation. And that pattern seems to sort of look like this one right here. If we kind of reverse the order of that part of the series, we see it has double, single, carbocation, and then we see the carbocation separated from the double bond by a single bond. Therefore, this molecule is also going to have some resonance. Okay, so hopefully that gives you some intuition as to how you can identify where the resonance is in a molecule. Okay, in a separate video, I'll actually look at how you characterize the resonance in these two aromatic compounds, although recognizing aromaticity is not critical at this point in most courses.